This is lecture number 5 and part 2. In this lecture, I will talk about the classifications of heat exchangers, and we will develop the awareness of the fouling on different surfaces, and we will also determine the overall heat transfer coefficient for a particular heat exchanger, and then I will perform the general energy analysis on the heat exchangers. Further, I will develop a relation for the logarithmic mean temperature difference for the use in the Lmtd method, and to modify it for different types of heat exchangers using correction factors for different geometries. And then later on I'll talk about the relationship for the effectiveness, and the analysis of the heat exchanger will be performed when the outlet temperature is not known. And this will be done by an effectiveness Ntu method. And finally, at the end, I will discuss about the selection of the heat exchangers and the pressure drop calculations in the heat exchanger, as well as the fouling phenomena in detail, and some numerical problems at the end. Let's have a look on the types of the heat exchangers. Different heat transfer applications requires different types of hardware and the different configurations of heat transfer equipment. The attempt to match the heat transfer hardware to the heat transfer requirements within the specified constraints has resulted in numerous types of innovative heat exchanger designs. And in this slide, we will see the simplest design of the heat exchanger that will be called as the double pipe heat exchangers. The double pipe heat exchangers mainly consist of two pipes. One is the inner pipe and the one is known as the outer pipe, right? And the one fluid in the double pipe heat exchanger flows through the smaller pipe, while the other fluid flows through the annular space between the two pipes. What is the annular space? If this is the inner pipe and this is the outer pipe, the space between the outer and the inner pipe is known as the annular space, right? So two types of flow arrangements are possible in a double pipe heat exchanger. For example, the first one is in parallel flow, as you can see in this diagram. So for example, the hot fluid is moving in the smaller pipe or the inner pipe in this direction from left to right, and the cold fluid is also moving in the right direction. So both of the fluids, hot and the cold fluid, are moving in the same direction. So this kind of heat exchanger is known as the parallel flow double pipe heat exchanger. While in case of the counter flow heat exchanger, double pipe heat exchanger, the hot fluid is moving from left to right, and the cold fluid is moving from right to left. So both of the fluids are moving in opposite directions. So this is the example of the double pipe heat exchanger with the counter current flow, right? And let's have a look on the temperature profiles of the parallel flow and the counter flow heat exchanger, double pipe heat exchanger. So this is a temperature profile of the parallel flow double pipe heat exchanger. So as both the fluids pass through the double pipe heat exchanger in a parallel flow pattern, the temperature of the cold fluid increases, right, and the temperature of the hot fluid decreases, right? And these two lines never pass each other, right? So it will not happen that this black line moves over here and this pink line will move over here. This will never happen, right? So this is the profile which is known for the parallel flow double pipe heat exchanger, and this is the temperature profile for the double pipe heat exchanger with the counter current flow. As the cold fluid is moving from this point, so this is the initial point of the cold fluid, right, and this is the initial point of the hot fluid as the hot fluid is moving from this point. So as both of the fluids will pass through the heat exchanger or the double pipe heat exchanger, what will happen? The temperature of the hot fluid decreases and the temperature of the cold fluid increases. So this is the temperature profile for the double pipe heat exchanger with the counter current flow. So another type of heat exchanger which is specially designed to realize a large heat transfer surface area per unit volume, and that kind of heat exchanger is known as the compact heat exchanger, right? The ratio of the heat transfer surface area of a heat exchanger to its volume is called the area density, which is represented by this beta. A heat exchanger with the area density greater than 700 meter square per meter cube is classified as being compact heat exchangers. So the example of compact heat exchangers are car radiators. In that example, the area density is 100 meter square per meter cube, and for the regenerator of a Stirling engine, this area density is 15,000 meter square per meter cube. And for the human lungs, this beta value is nearly equal to 20,000 meter square per meter cube. Compact heat exchangers enables us to achieve the high heat transfer rate between the two fluids in a small volume, and they are commonly used in the application with the strict limitations on the weight and the volume of heat exchanger. Another classification of the heat exchanger based upon the flow directions, right? So let's have a look on the cross flow heat exchanger. In the compact heat exchanger, the two fluids usually move perpendicular to each other, right? The cross flow is further classified as the unmixed or the mixed flow, right? So this is the particular example of the compact heat exchanger in which the two fluids are moving perpendicular to each other, and as you can see that the one fluid is moving in these pipes, and the another fluid is moving at the perpendicular direction through these vertical plates. So the fluid which is moving through these vertical plates are unmixed with each other, right? So both of the fluids, right, which are moving perpendicular to each other are unmixed, right? And the second classification is the one fluid is mixed and the one fluid is unmixed. So the fluid which is moving through these pipes, right, is considered as unmixed because it is not mixing with any other fluid. And the second fluid which is moving in a cross direction or moving at the perpendicular to this flow direction is the mixed flow, right? So the fluid layer which is moving over here, and after passing through it might go from here and it might go from here. So the flow will mix while it passes through these tubes. So the most common type of heat exchanger in the industrial application is the shell and tube heat exchanger, as you can see in this diagram. Shell and tubes heat exchanger contain a large number of tubes, and these are the tubes, right? Sometimes several hundred packed in a shell with their axis parallel to that of the shell. Heat transfer takes place as one fluid flows inside the tube while the other fluid flows outside the tubes through the shell. So there are some vertical plates which are known as baffles, and baffles are commonly placed in the shell to force the shell side fluid to flow across the shell and to enhance the heat transfer and to maintain the uniform spacing between the tubes. Despite their widespread use, shell and tube heat exchangers are not suitable for the use in automotive and the aircraft application because of their relatively large size and weight. And the tubes in the shell and the tube heat exchanger open to some large flow rates are called headers, and at the both ends of the shell, where the tube side fluid accumulates before entering the tubes and after leaving the tubes. So this is called the rear head and this is called the front head. There are different classifications of the rear head and the front head, and I will explain it in the upcoming slide. So the shell and tube heat exchangers are further classified according to the number of shell and the tube passes involved. So the heat exchanger in which all the tubes makes one U-turn in the shell, as you can see in this diagram, right, for example, are called the one shell pass and the two tube passes heat exchanger, right? So the fluid is moving in the shell side and it will just pass from the shell side. This is called the one shell pass, right? And the tube which in which the fluid is entering at this point, and it will start its journey from this point to this point. This is called one pass, and from this point to this point, and it will move out. This is called the second pass. So the fluid which is moving in the tube side will complete the two passes. So this configuration is known as one shell pass and the two tube passes configuration of the heat exchanger. Similarly, and this is the different configuration in which two shell passes and the four tube passes. As the fluid is moving in the shell side at this point, the fluid will enter and it will flow from this point to this point. It will complete one pass, and from this point to this point, and then it will move out. And from the shell side, the fluid is completing two passes, so that's why it is called two shell passes. And in the tube side, when the fluid is moving, entering in the tube side, it will complete four passes: the one pass, the second pass, and the third pass, and the fourth pass. And so this configuration is known as the two shell pass and the four tube pass configuration of the shell and tube heat exchanger. So this type of configuration is known as the multi-pass flow arrangements in the shell and tube heat exchanger. So there are some other classifications of the heat exchangers. For example, the regenerative heat exchanger involves the alternate passage of the hot and the cold fluid streams through the same flow area. And the dynamic type regenerator involves a rotating drum and the continuous flow of the hot and the cold fluid through different portion of the drum, so that any portion of the drum passes periodically through the hot stream, storing the heat, and then through the cold stream, rejecting the stored heat to another stream. So I have already explained the regenerative and the recuperative type of heat exchanger in the previous lecture. So the next is the condenser. One of the fluids is cooled and condenses as it flows through the heat exchanger, and the boiler is one of the fluid absorbs the heat and vaporizes. So an innovative type of heat exchanger that has found widespread use is known as the plate and frame heat exchanger, as you can see in this diagram. And it consists of a series of plates with corrugated flat flow passages. The hot and the cold fluids flow in the alternate passages, as you can see here, right? If the hot fluid is moving over here and the cold fluid is moving at this in this portion, right? And hot fluid and the cold fluid. So alternatively, hot and the cold fluid is passing through this plate and frame heat exchanger. So each cold fluid stream is surrounded by the two hot fluid streams, resulting in a very effective heat transfer. The plate and frame heat exchanger can grow with increasing demand for the heat transfer by simply mounting more and more plates in the configuration. So they are well suited for the liquid to liquid heat exchanger applications, provided that the hot and the cold fluid streams are at about the same pressure. On the topic that is known as the overall heat transfer coefficient. This is very important topic that will be used and it will be helpful for the design of the heat exchanger in the upcoming lectures. A heat exchanger typically involves the two fluids separated by a solid wall. The heat is first transferred from the hot fluid to the wall by the convection process, number one, and then the heat is conducted through the wall, that is the second process, and from the wall to the cold fluid again by the convection process, this is called third process. So the transfer of heat from the hot fluid to the wall and then through the wall and then from wall to the cold fluid, there are three processes and two convection processes, and the one is known as the conduction process. For example, this is a double pipe heat exchanger, and this inner pipe has the hot fluid and the annulus area has the cold fluid, right? And first of all, what will happen, the heat will transfer from this hot fluid to the wall, and this is known as the convection process, and the heat will be conducted through the wall, right? And this will be known as the conduction process, and from the wall to the cold fluid, this is called the again convection process, right? And for example, this is the extended or the elaborated diagram in which you can have a look on this temperature Ti, which is the higher temperature at the inner tube or the inside of the inner tube. And first of all, the heat will be transferred from this point to this point, from the hot fluid towards the wall of the tube, inner tube, right? So this process is known as the convection process, right? And then the heat will be conducted from within the wall, right? So this will be the conduction process, and from this point to this point again the heat will be moved from the wall towards the cold fluid by the convection process. So from this point to this point the heat will be traveled. So there will be two convection processes and the one conduction processes. So the fluid will face the three kind of resistances, and the one is by the convection process, and the one is through the wall, and one is by the convection process when the heat will be transferred from the wall to towards the cold fluid. So the resistance of each phase is connected with the convective heat transfer coefficient multiplied by its area, right? So AI is the inner surface area of the inner tube, and HI is the convective heat transfer coefficient, and this is the resistance of the wall, right? And R0 is the outer resistance, and which is connected with the inversely proportional to the product of convective heat transfer coefficient and the outer surface area. So this R wall, which is the resistance of the wall, is basically represented by this formula, and here L is the length of the tube and K is the thermal conductivity of the material with which the wall is made, and D0 and the Di are the outer and the inner diameter of the inner wall, right? And the description is also mentioned over here. There are two convection processes and the one is the conduction process. I have already explained in this diagram. So if we want to determine the overall resistance for the fluid, for the heat which is moving from this point to this point, from this higher temperature to this lower temperature, and the overall resistances can be determined, or the total R total can be determined by adding all the resistances, the inner resistance and the wall resistance and the outer resistance. So adding all the resistances, we will have the overall resistance. So the inner area of the tube is simply determined by this formula, and the outer area of the tube is simply represented by this formula. Here I and O are represented for the inner side, and O represents for the outer side. So this is a topic which is explaining about the thermal resistance network associated with the heat transfer in a double pipe heat exchanger. So in the analysis of the heat exchanger, it is convenient to combine all the material resistances in the path of the heat flow from the hot fluid to the cold fluid into a single resistance, which is known as R, right, which is mentioned over here. And to express the rate of heat transfer between the two fluids is represented by this formula. Rate of heat transfer is directly proportional to the temperature difference and inversely proportional to the resistance, or we can simply say that the rate of heat transfer is equal to U, which is known as the overall heat transfer coefficient. A is the surface area and delta T is the temperature difference, and U here is simply known as the overall heat transfer coefficient, which has the unit of watt per meter square per degree centigrade. So this overall heat transfer coefficient has the unit of watt per meter square per degree centigrade, and it is similar to the ordinary convection heat transfer coefficient, which is represented by H, and it has the same units. So if we cancel the delta T from this equation, we will ultimately come up with this equation, right? So, and perhaps you are wondering why we have two overall heat transfer coefficients, UI here and the U0 for a particular heat exchanger. The reason is that every heat exchanger has the heat transfer surface area such as AI, which is for the inner surface area, and A0, which is the outer surface area, and these surface areas are not equal. So that's why we have two different heat exchanger, two different surface areas, and AI and A0, right? So here one thing is very important, that the product of the overall heat transfer coefficient for the inner fluid and the inner surface area is equal to the product of the overall heat transfer coefficient and the surface area for the outer tube, right? But keep in mind that the products are same, but it does not mean that their overall heat transfer coefficients are same. UI and U0 are not equal until or unless their areas are same, right? So there is a special case that when we have a particular heat exchanger whose whose thermal conductivity is very high. And let's have a look on this diagram. For example, this is a hot fluid and there is a cold fluid in the annulus, and if we assume that this wall, which is in between the hot and the cold fluid, is very thin, right? So what does it mean? What does it mean? The inner diameter and the outer diameter is almost same. If this wall between the cold and the hot fluid is very thin, so what does it mean? We will assume that the di and the d naught are same. Ultimately, the inner surface area and the outer surface area will also be same. So for this case, in which we are considering that the wall with which the material is made is very thin and it has very high thermal conductivity, for that case we assume that the resistance of the wall will be considered as 0, and we are considering that the thickness of the wall is very thin, so we are also assuming that the inner surface area and the outer surface area are almost same, so we just represent it by simple AS. So this equation will become ultimately reduces to this equation, right? And after putting these conditions, right, so the above equation, this equation ultimately reduces to this equation, right? How? But have a look on this. If we put our wall, this will be equal to 0, right? And instead of putting AI and A naught, we are putting AS. We put AS over here and we put AS over here, right? And what will happen next? We will take common AS from this side, and from this side, and ultimately this whole equation will reduces to this equation. And we are just assuming that the overall heat transfer coefficient nearly equal to the overall heat transfer coefficient for the inner fluid and the overall heat transfer coefficient for the outer fluid. Here the one thing is very important that I will explain it in a bit. For example, the overall heat transfer coefficient U, this overall heat transfer coefficient U is dominated by the smaller convection coefficient. When one of the convection coefficient is much smaller, this is one convection coefficient for the inner fluid, this is the convection coefficient for the outer fluid, right? So if the convection coefficient is much smaller than the other one, for example, if we say that the HI is very small than the H naught, so in this equation we say that if HI is very small then H naught, what will happen if this is let me just explain it with the digital values. For example, if this is 0.1 and this is 10, so if we solve this portion, right, so 1 over 0.1 will be equal to 10 and 1 over 10 will be equal to 0.1. so ultimately the coefficient which is smaller will have the higher contribution towards the overall heat transfer coefficient. So this is what it is mentioned over here, that the convection coefficient which is smaller than the other one, for example HI is very small than the H naught, ultimately if we solve it, then 1 over H naught will be very high as compared to 1 over HI will be very high as compared to the 1 over H naught. Ultimately U will be dominated by the convection coefficient which is very small, so U will be nearly equal to the HI which is the smaller one. When we solve it, ultimately this overall heat transfer coefficient will be dominated by the inner convection coefficient. This situation arises frequently when one of the fluid is a gas and the other fluid is liquid. In such cases, fins are commonly used. Fins are some extended surfaces which are usually installed on the heat exchanger, usually on the gas side, to enhance the product of overall heat transfer coefficient and the surface area and the heat transfer on that side. The overall heat transfer coefficient, which is represented by U, ranges from about 10 watt per meter square per degree centigrade for gas to gas heat exchangers to about 10,000 watt per meter square per degree centigrade for the heat exchanger that involves the phase change phenomena. So this is the list which shows that the range of the overall heat transfer coefficient. As you can see that the smallest value is for the gas to gas heat exchanger, and the largest value will be for the feed water heaters in which the phase change is involved. So it ranges from 1000 to 8500 watt per meter square per Kelvin. So when the tube is finned, what does it mean? When the tube is basically the extended surfaces are basically installed on the tube side. So on one side, to enhance the heat transfer rate, and the total heat transfer surface area on the fin side will be equal to this formula. So we usually say that the surface area is represented by AS. So if we install the extended surfaces on the tube side, on the outer surface of the tube or inside of the tube, what is going to happen, that the total surface area would be the area of the fins or the area of the extended surfaces, and the area which is unfinned, or the area of the tube at which the extended surfaces are not placed or not installed. So the empty surface area and plus the extended area of the surfaces which are basically installed on the tube. So the total surface area, which is represented by AS, will be determined by adding the fin surface area or the unfinned and the unfinned surface area. So for the short fins of high thermal conductivity, we can use this total area in the convection resistance relationship as is given over here. So usually when we install the external surfaces on a particular heat exchanger, so there is some efficiency that the extended surfaces or the fins are efficient up to some percentage. So we have to add the fin efficiency as well when we determine the overall surface area. So we just incorporate the thermal efficiency or the efficiency of the fins in this formula for the total surface area. For example, if we install the external surfaces on a tube outside of the tube, so if the extended surfaces or the fins are efficient only 60%, so that's why we have to multiply 0.6 with the surface area of the fins, right? So it depends upon the efficiency of the fins that we are installing, and it ultimately also depends upon the geometry of the extended surfaces or the fins that we are installing outside the heat exchanger. So another important factor which is known as the fouling factor. The performance of the heat exchangers usually deteriorates with the time as a result of the accumulation of deposits on the heat transfer surfaces. The layer of deposits represents the additional resistance to the heat transfer. This is represented by the fouling factor, and this is sometimes represented by RF. So this is a usual case when you boil the water in a particular pan at your home. You sometimes see the after the boiling, the inner surface of the pan is somewhat becomes like a white surface. This is due to the deposition of the salts which were present in that particular water. When you boil that water, the dissolved salts will become settled down and stick to the inner surface of the pan. So if the same phenomena happens in the heat exchangers, so this accumulation grows up and ultimately it will add the resistance towards the heat transfer. So this is the precipitation of the ash particles on the superheater tubes. As you can see that these are the deposits which resist the transfer of heat across the particular wall or across the particular tube. So when we design the overall heat transfer coefficient, so we have to add this resistance as well. This is because of the deposition of the salts on the inner or the outer surfaces of the tube. For example, if we have the double pipe heat exchanger, so the surface which involves the transfer of heat is the inner surface, right? So we have to incorporate the two resistances, right, for the fouling factor. So this is the formula that we have already seen, that, right, the resistance, overall resistance formula. So this is the convective resistance for the inner pipe, and this is the convective resistance for the outer pipe, and this is the conductive resistance for the wall through which the heat is conducted. So this is the additional resistance because of the deposition of salt inside the inner tube, right, and this is the additional resistance which is due to the deposition of salt on the outside of inner tube, right. So pay attention on my words, so I will repeat it again. This is the resistance which is due to the deposition of salt on the inner side of the inner tube, right, or this is the additional resistance which is provided by the accumulation of salt on the outside of the inner tube, right. So this fouling factor increases with the operating temperature and the length of the surfaces, and decreases with the velocity of the fluid. So if you use sometimes the high velocity fluid, so the deposit salts or the deposit materials will wash away with the high velocity fluids. I will explain it in the upcoming topic, that how we can reduce the fouling and how can we overcome this fouling in the heat exchanger. There are multiple phenomena or multiple parameters with which we can control this fouling, right. And the length of service, another important parameter, that if you are using the heat exchanger for last 6 months, so there may be the less fouling, or if we are using the particular heat exchanger from last 6 years, so there may be the chance that there may be the high amount of the fouling inside the heat exchanger. So this is the table which shows that for the fouling factors or the thermal resistances due to the fouling are for a unit surface area. So this is the RF values for the fuel oil, that will be equal to 0.0009, and it has a unit of meter square Kelvin per watt. So keep in mind that the units are very important to keep in mind, that because you are going to use this RF value when you design the double pipe heat exchanger or the shell and tube heat exchanger. So keep in mind that for example, if the oil is moving, right, so it has a value of 0.0001. For the air, its value is 0.0004 RF, the value of the fouling factor. The analysis of the heat exchanger. This is very important topic. An engineer often finds himself or herself in a position to select a particular type of heat exchanger that will achieve a specified temperature change in a fluid stream of non-mass flow rate, and this is usually done by the process which is known as the log mean temperature difference method. So this is the first way to select a particular heat exchanger, and the second is to predict the outlet temperatures of either hot fluid or the cold fluid streams in a specified heat exchanger. So this is done by the second method, which is known as the effectiveness Ntu method. I will discuss in detail about the Lmtd method and the Ntu method. So first of all, let us consider we have the counter current double pipe heat exchanger, right. So this is the temperature profile for the counter current flow, right. So what does it mean? The counter current flow means the cold fluid is moving in one direction and the hot fluid is moving in opposite direction, right. And with the passage of time, when the cold fluid enters, it has a lower temperature. When the cold fluid exits the heat exchanger, it will have the high temperature. Similarly, the hot fluid at the entrance will have the high temperature, and at the exit, hot fluid will have the low temperature, right. So for this case, the rate of heat transfer in the heat exchanger is given by these two equations, right. But assuming that the heat exchanger is fully insulated, no heat is being transferred to the environment, right. So there is only the heat exchange between the hot fluid and the cold fluid. So the one thing is the heat is only transferred from the hot towards the cold fluid. So the heat transfer rate for the cold fluid is given by this expression, which is known as the Q dot mCp delta T, right? mC is the mass flow rates, CPC is the specific heat, and this is the temperature difference, Tc out minus Tc in. For the cold fluid, the outer temperature is higher as compared to the inlet temperature, so that's why we have this expression. Similarly, for the hot fluid, that the Q dot is the mass flow, is the heat flow rate, rate of heat transfer, and the m dot h is the mass flow rate for the hot fluid. Cph is the specific heat for the hot fluid, and this is the temperature difference. So Th is the temperature of the hot stream at the inlet point, obviously it has the higher value, minus the temperature of the hot stream at the outlet of the heat exchanger, obviously this has a lower temperature. So this is the delta T for the hot stream. So one thing is very important to keep in mind, that the two fluid streams that have the same capacity rates, right, will experience the same temperature change in insulated heat exchanger. For example, the same capacity rate means both the fluids are same, right? So let's say both the fluids are water, so in that case both the fluid will have the same capacity rates, right? So if both the fluids are same, so the delta T among these two hot and the cold stream will be same at each point, right? Delta T will be same at this point, delta T will be same at this point, delta T will be same at this point. So this is only for the condition that both the fluids are same, right, or the same capacity rates, and the heat exchanger is fully insulated. So the one thing is that we are adding over here that the product of the mass flow rate and the specific heats are simply known as the heat capacity rate. So if we multiply the mass flow rate and the specific heat, we will ultimately get the heat capacity rate for the hot fluid, and similarly the heat capacity rate for the cold fluid. And if we substitute these two equations in the above two equations, we will ultimately come up with this equation, that the heat transfer rate is equal to the heat capacity rate for the cold fluid multiplied by the temperature difference for the cold fluid. And similarly, this is the heat transfer rate for the hot fluid is equal to the heat capacity rate, right, multiplied by the temperature difference for the hot fluid. So the rate of evaporation and the rate of condensation for the particular fluid is determined by this formula. The Q dot is equal to m dot multiplied by HFG. M dot is the mass flow rate, right, and the rate of evaporation or the rate of condensation, or the HFG is the enthalpy of vaporization of the fluid at the specified temperature or pressure. We cannot use this formula, cannot use this formula either for the determination of the rate of condensation or the rate of evaporation. So this is the reason behind this. First of all, let us just try to understand that the condensation process or the boiling process. So for example, this is the heat exchanger, that is the inlet and the outlet, and this is the hot fluid and this is the cold fluid, right, and this is the condensation case, right. So these are the vapors, right, these are the vapors which are entering at this point and leaving at this point, right, and this is the cold fluid which is entering at this temperature and leaving at the higher temperature. So during the condensation process, what is going to happen, that the vapors which are condensing into the liquids, and its temperature is not changing, its temperature is constant, right. This horizontal line means the temperature is constant for the fluid or for the vapors which are condensing into the liquids. So what is happening in this case, that the vapors which are entering at this point in the heat exchanger or at the inlet of the heat exchanger will give their heat or the latent heat, right, the latent heat will give it to the cold fluid, and the temperature of the cold fluid will increase, but the condensing vapors which are condensing into the liquid, and its temperature will remain constant, because you need to understand that there are two kinds of heat. The one is known as the latent heat, and the one is known as the sensible heat. So if the sensible heat changes, then the temperature will change. So in that case, in the condensing vapors, there is only the latent heat. When the latent heat changes, only the phase change occurs and the temperature remains constant, right? So the temperature change is associated with the sensible heat. When there is a change in the sensible heat, then there will be the temperature change, and when there is a change of the latent heat, then there will be the change of phase while the temperature remains constant. So in this phenomena of the condensation, what is going to happen that there is no change in the temperature, but there is the change in the phase, right? So the vapors which are condensing by releasing the heat to this cold fluid, and this heat is actually known as the latent heat, and the temperature remains constant, right? And this is the case of condensation. But when you see the case of the boiling process, right? So this is the opposite case, right? Let's say this is the case of boiling, right? In this case, that the hot fluid is at the higher temperature while entering into the heat exchanger. So this is our primary fluid that we want to boil, right? So this is the fluid which is entering at the heat exchanger at this point, right? And we want to boil this fluid, right? So what is going to happen for the boiling of this fluid? We need some heat. So the heat is being provided by the hot fluid, right? When the heat is being taken from the hot fluid, obviously the temperature of the hot fluid along the length of the heat exchanger will decrease, right? So at the entrance, the hot fluid will have the higher temperature, and at the exit, the hot fluid will have the less temperature. But what is going to happen that this heat which is taken from this hot fluid to the boiling fluid, so this heat is being used to boil the fluid or to convert the liquid into the vapor state, right? So this is again the latent heat, right, which is taken up by this boiling fluid to change its phase from liquid to vapors, but its phase or its temperature will not change, and its temperature will remain constant. Similar is the case of boiling. So what will happen when you boil the water, right, at 100 degrees centigrade, when the temperature of the water will reaches at 100 degrees centigrade, and it will never increase. Whatever the amount of heat that you will provide to that particular amount of water, the boiling temperature of the water at 1 atm pressure will not increase. So the amount of heat that you are providing to the boiling water will goes into the latent heat, and that liquid that converts the liquid into the vapor phase, that the extra amount of heat that you provide during the boiling process. So this is the condensation process, and this is the boiling process in the heat exchanger. So for that case, either in case of condensation process or in case of the boiling process, the heat capacity rate, right? The heat capacity rate in case of condensation process, or the heat capacity rate for the boiling process approaches to infinity, because there is no temperature change, or the temperature change is zero. So in that case, the heat capacity rate approaches to infinity. So we cannot use the previous formula which is mentioned in the previous slide. So we have to use this formula, that the Q dot is equal to the rate of evaporation, or the rate of condensation is equal to multiply by the enthalpy of vaporization. I believe that I have used this formula in one of the numerical that has been given in the previous lectures. So you can go through that numerical formula, so that you will get the idea how to use this formula to determine the rate of evaporation, or to determine the rate of condensation. So previously I have already explained that the temperature difference between the hot and the cold fluid varies along the length of the heat exchanger. So it is convenient to use or to have the mean temperature difference, which is represented by delta Tm, for the use in this relationship, that is Q dot is the heat transfer rate is equal to the overall heat transfer coefficient, As is the surface area of the heat exchanger, and the delta Tm. So we know that the delta T, which is the temperature difference, varies along the length of the heat exchanger, right? And let me just show you on the previous diagram, this diagram, right? So this is the parallel flow heat exchanger. So as you can see that this delta T at the start of the heat exchanger is very high, and the delta T at the end of the heat exchanger is very small. So this delta T varies along the length of the heat exchanger. So in order to use this expression, right, so to use this expression, we need to develop an expression for the delta Tm where it will give us the average value of the delta T or the temperature difference along the length of the heat exchanger. So we will develop the expression for the log mean temperature difference method, and to develop the expression for the delta Tm over here, I will explain it in a bit, all this derivation. I'm just trying to give you the idea that why we are using this, or why we are going to solve this, or why we are going to develop the expression for the delta T Lm, or the log mean temperature difference. The reason is that the delta T varies along the length of the heat exchanger. If it varies along the length of the heat exchanger, so as you can see in this formula, that we know the heat transfer rate, and we know the overall heat transfer coefficient, and if we want to determine the surface area of the heat exchanger, so this must be some average value, or this must be the constant value, right? And we need to know that the average value or the constant value of delta Tm along the length of the heat exchanger. So if we know all the values Q dot, U, and delta Tm, so we must get the value of the heat transfer surface area, so that we will have the correct value of the heat transfer surface area. So what does it mean? That if the delta T is very small at some point of the heat exchanger, so the surface area will be different. If the delta T is very large at some point of the heat exchanger, the surface area would be different. So this delta T will have the impact on the surface area. So the ultimate objective of the log mean temperature difference method is to determine the surface area by specifying a specific formula for this delta T, and this delta T would tell us that this is the temperature difference along the length of the heat exchanger, and we will use some average value of this delta T, right, in order to get the value of the surface area. So for the determination of, or to develop this expression for the Lmtd, delta T Lm, or the log mean temperature difference, so we will just perform this derivation. Before going into detail, let's have a look on this diagram. First of all, this is the double pipe heat exchanger with the parallel flow, right? So the cold fluid is entering over here and leaving over here, and the hot fluid is entering at this point and leaving at this point. So both of the fluids are moving in the same direction. So this is known as the parallel flow double pipe heat exchanger. So we will just consider this control volume over here, right? So we will perform the energy balance on this control element, right? So then we will develop this expression, right? So let's have a look on the temperature profile for the parallel flow double pipe heat exchanger. So this is along the length of the heat exchanger, though this is the starting point of the heat exchanger at the x-axis, and this is the ending point of the heat exchanger on the x-axis. So this is 0.1 and this is 0.2, and this is the temperature axis, right? So from bottom to top, temperature is increasing. So in case of the cold fluid, right, which is entering at this point of the heat exchanger, has a lower temperature, and along the length of the heat exchanger, the temperature of the cold fluid rises, right, or increases. And for the case of the hot fluid, when it moves along the length of the heat exchanger, its temperature will decreases, right, and ultimately it comes out at this temperature. So the inlet temperature of the cold fluid is the lower temperature, and the outlet temperature of the cold fluid temperature is the higher temperature. While in case of the hot fluid, the inlet temperature is the higher temperature, and for the hot fluid, the outlet temperature is the lower temperature, right? So we will just develop an expression for the delta T, which will be the average of the delta T value along the length of the heat exchanger. As you can see that at this point, the delta T at point 1, the delta T would be very high, right? But at the point 2, the delta T, the temperature between the hot and the cold fluid, is very small. So along the length of the heat exchanger, this delta T varies, right? And it will have a huge impact when we design the heat exchanger, or when we go for the determination of the surface area, right? So for this, for the determination or for the development of this expression, log mean temperature difference, so we will just assume this small control element, right, and we will perform the energy balance, right? So this is the control element, right? This is the control element over which we are performing our energy balance. For example, this is the control element, right, from this point to this point on the cold fluid stream, and this from this point to this point, this is on the hot fluid, right? So first of all, we will have a look on the energy balance or the energy change, right, in the hot fluid stream from this point to this point in this control element, right? So at this point, the temperature is slightly higher, but at this point the temperature is slightly lower, because we are applying the energy balance on this control element. So first we will have a look on the energy balance on this control element at this hot fluid stream, right? So the temperature change along the hot fluid in this control element is delta TH, right? And for the cold fluid, the temperature change, right, during this control element is delta TC. So delta TC is the temperature change in this control element for the cold fluid stream, and delta TH is the temperature change for the hot fluid in this control element, right? And one thing that you need to keep in mind that we will write the expression for the energy balance. So the rate of change of energy is equal to m dot h, and the mass flow rate for the hot fluid, and the specific heat, and the delta TH, which is the temperature change. So keep in mind that this delta TH is the negative quantity. Why? Because when we open this delta TH, the final temperature is the lower temperature and the initial temperature is the higher temperature. So when we determine the delta T, which is delta TH, is the final minus initial. If the final temperature has the lower value as the initial temperature has the higher value, so this delta TH will be the negative quantity. So what does it mean? It means that this delta TH, or the temperature change in the control element along the hot fluid stream, is the negative quantity, and to make it positive we are just putting negative sign over here. This is the negative quantity. In order to make it positive, so we put negative sign over here. This is the energy balance over the control element in the hot fluid stream, and this is the energy balance for the control element along the cold fluid stream, right? So we just rearrange this equation into this one. So we'll take delta TH on one side and keeping all the other parameters on the right hand side. Similarly, from this expression we just take delta TC on the left hand side and all the other parameters on the right hand side, right? And we will take the difference of these two equations. We'll take the difference, delta TH minus delta TC, right? So after taking the difference of these two equations, right, we will ultimately come up with this expression. So this is one of the main expression, right? This is one of the main expression, and ultimately this is the longest equation that we have just developed after putting the energy balance on the hot fluid stream and the cold fluid stream separately, and then take the difference. We will ultimately come up with this expression, right? And there will be the heat transfer, right, between the hot fluid stream and the cold fluid stream, right? So this heat transfer, which is represented by this delta Q dot, right, and it is simply represented by this expression. So this is the energy transfer from the hot fluid towards the cold fluid. So this is the expression which is mentioned over here, or simply it can be the rate of heat transfer in the differential section of the heat exchanger. So this is the final expression, and the rate of heat transfer between the rate of heat transfer in the differential section is given by this expression. So this is delta Q dot. We will put this delta Q dot over here, and after simplifying that we will come up with this expression. If we take the integration on this equation on both hand side, we will ultimately come up with this expression, right? So in this expression we have this m dot h, the mass flow rate for the hot fluid, and the specific heat for the hot fluid, and the mass flow rate for the cold fluid, and the specific heat for the cold fluid. So if we put the values of this the specific heat, the product of these two quantities is the specific heat capacity rate, and the product of these two is known as the heat capacity rate for the cold fluid and the heat capacity rate for the hot fluid. If we put the values of this heat capacity rate for the hot fluid and the cold fluid from the expression which is mentioned over here, right, from here, right, from these two expressions, we will just take the values of m dot c cpc, m dot h cph, from taking these two values from these two expression, and after putting over here, and we will ultimately come up with the expression which is known as delta T Lm is equal to the delta T1 minus delta T2 divided by natural log of the ratio of delta T1 over delta T2, which is known as the log mean temperature difference. So this is the expression for the log mean temperature difference, and which is suitable for of the average temperature difference for the use in the analysis of heat exchangers, where the delta T1 and the delta T2 represents the temperature difference between the two fluids at the two ends, such as the inlet and the outlet of the heat exchangers. It makes no difference which end of the heat exchanger is designated as inlet or the outlet. So this is a parallel flow geometry or parallel flow configuration of the double pipe heat exchanger. The temperature difference between the two fluids in case of parallel flow configuration decreases from delta T1, which is what is delta T1 is the temperature difference at one end of the parallel flow heat exchanger, and the delta T2 is the temperature difference at the end of the heat exchanger. So at the start, delta T1 is very high and delta T2 is very small, as you can see from this temperature profile, right? This is the parallel flow configuration, but as you can see at the start, delta T1 is very high and delta T2 is very small in case of parallel flow configuration of the heat exchanger. So it is tempting to use the arithmetic mean temperature, which is simply determined by taking the average of delta T1 plus delta T2 divided by 2. We will ultimately get by the temperature that is called the arithmetic mean temperature difference. So it is the mean or the average temperature difference, while that the expression that we have developed in the previous slide, the logarithmic mean temperature difference, which is represented by the delta T Lm, is obtained by tracing the actual temperature profile of the fluids along the heat exchanger and is an exact representation of the average temperature difference between the hot fluids and the cold fluids, and it truly reflects the exponential decay of the local temperature difference. Note that the delta Tm is always less than the delta Tlm is always less than the delta Tm, right? Therefore, using delta Tam or the arithmetic mean temperature difference in the calculations instead of log mean temperature difference will overestimate the rate of heat transfer in the heat exchanger between the two fluids, right? So keep in mind that we will ultimately have to use this Lmtd or delta Tlm, right? If we use this one, the simple arithmetic mean temperature difference, it will give you the higher value of the or rate of heat transfer in the heat exchanger. So if there will be the high rate of heat exchanger, and it will give the wrong value of the surface area of the particular heat exchanger, because in this method the ultimate objective is to determine the overall surface area of the heat exchanger. So using the true value of the delta T, which is the delta Tlm, is the right way to determine the true value of the rate of heat transfer in the heat exchanger between the two fluids to get the actual surface area for a given heat exchanger. So when we use delta T1, or the delta T1 differs from delta T2 by no more than 40%, the error in using arithmetic mean temperature difference is less than 1%, right? But error usually increases to undesirable levels when the delta T1 differs from delta T2 by greater amounts. Therefore, we should always use the logarithmic temperature difference when determining the rate of heat transfer in a particular heat exchanger. So in the previous slides, I have developed an expression for the log mean temperature difference for the configuration in a parallel flow double pipe heat exchanger. On the similar ground, you can develop the expression for the log mean temperature difference for the double pipe heat exchanger with the counter current flow. So as I'm not going to develop the expression for the counter current flow for the double pipe geometry, but I will explain some point that the Lmtd or the delta Tlm is preferable for the counter flow current in the heat exchanger design, right? So let's have a look on the counter current flow in the double pipe heat exchanger, right? This is double pipe heat exchanger. The hot fluid is moving in the right direction and the cold fluid is moving in the left direction. When you see the temperature profile, right? So initially the hot fluid is at the higher temperature, and ultimately with the passage of time, when it exits the heat exchanger, it will at the lower temperature. And similarly, when the the cold fluid enters into the heat exchanger, it is at the lower temperature with the passage of time, and when it will exit, it will have the higher temperature. So this is the increase in the cold fluid temperature and the decrease in the hot fluid temperature is due to the exchange of heat between these two streams. So the temperature difference is delta T. So this is the temperature profile. The delta T at this point is different. The delta T at this point is different. So on the similar ground that we developed the expression of the log mean temperature difference in the previous slide for the parallel flow, so on a similar ground you can develop the expression for the counter current flow. In the limiting case, the cold fluid will be heated to the inlet of the hot fluid temperature, right? So this is the cold fluid. So the maximum possibility is that this cold fluid will be heated up to this temperature, and this is not always the case. This can only be possible that if the heat exchanger length is very large, right? So in case of very large length heat exchanger, this is only possible that the outlet of the cold fluid is approaching towards the inlet temperature of the hot fluid stream. This is never going to happen that, but this is the limiting case that I am discussing over here. However, the outlet temperature of the cold fluid can never exceed the inlet temperature of the hot fluid. So this outlet of the cold fluid will never goes up towards this temperature, right? It might achieve this temperature, might get at this point, but it will never exceed this temperature, and this will against the laws of thermodynamics. For the specified inlet and the outlet temperatures, the delta T Lm for the countercurrent flow heat exchanger is always greater than the parallel flow heat exchanger. So this is the expression that you need to keep in mind, that the delta T Lm for the countercurrent flow, Cf the counter flow, is always greater than the log mean temperature difference in case of parallel flow. So in this case, a smaller surface area or the smaller heat exchanger is needed to achieve the specified heat transfer rate in the counterflow heat exchanger. So one thing that you need to keep in mind that as well, when the two heat capacity rates of the two fluids are equal, so the log mean temperature difference and the delta T1 at the inlet and the delta T2 at the outlet all are same. And cross flow heat exchanger, and when we use the logarithmic mean temperature difference, we have to use a correction factor, and that correction factor is simply represented by F, right? So this is the log mean temperature difference, right, for the counter flow, right? And when we have to use this delta T Lm or log mean temperature difference for different configurations, such as for the multipass and the cross flow heat exchangers, so we have to use the correction factor F. So the question is how to determine this correction factor, the value of this correction factor F. So in the previous slides, we have determined the value of the log mean temperature difference for the parallel flow and the counter flow only for the double pipe heat exchanger. But in most of the cases, we come across the heat exchangers which involves the cross flow as well as the multipass. So that's why we have to incorporate this correction factor, which is known as F. So the correction factor F depends upon the geometry of the heat exchanger and the inlet and the outlet temperature of the hot as well as the cold fluids streams. So this is, for example, a heat exchanger having a geometry of the multipass shell and tube heat exchanger with a cross flow, assuming that. So for this kind of geometry, for the heat transfer rate would be the Q dot, which is the heat transfer rate, is equal to the U, which is overall heat transfer coefficient, AS, that is the surface area, and we usually put delta T Lm, right? So here we are just introducing a new value or the new value which is known as the correction factor, and this correction factor must be used when you are using a heat exchanger with different configuration as compared to the double pipe heat exchanger. So when you are using only double pipe heat exchanger, either for the counter current flow or the parallel flow, you do not have to use this correction factor value, right? So you have to use the correction factor value F only for the configurations which involves the multipass and the cross flow heat exchangers. So the value F, which is the correction factor for common cross flow and the shell and tube heat exchanger configuration, is given in the figure versus two temperature ratios, right? So the one temperature ratio is P, capital P, and the second temperature ratio, which is known as R. So first of all, to determine the value of this correction factor f, we have to determine the value of these two temperature ratios. So first of all, we have to determine the value of P and the value of R. So this is the formula for the one temperature ratio, that is for P, and this is the formula for the second temperature ratio, which is known as represented by R. So here the four different temperatures are given, right? So capital T1, capital T2, small t1 and small t2. So in order to understand that what are these temperatures, so keep in mind that the 1 stands for the inlet and the 2 stands for the outlet, right? And capital T stands for the shell side and the small t stands for the tube side temperatures. So let's have a look on these two ratios. This is the first temperature ratio, which is represented by P, and this is the second temperature ratio, which is represented by R. For example, this is T2, which is the outside or the exit temperature of the tube, right? And this is the inlet temperature of the tube, right? And this is the inlet temperature of the shell, this is the inlet temperature of the tube. So capital T is used for the shell side, and 1 stands for the inlet and 2 stands for the outlet. So once you have the four temperatures, right, the cold fluid inlet temperature or the hot fluid inlet and outlet temperature, so let me just read it once again, that you must have four temperatures for a particular heat exchanger in order to get the value of correction factor, right? So if you have four temperatures, you can easily calculate the log mean temperature difference, right? Delta T Lm. And if you have these four temperatures, that the inlet of the hot stream and outlet of the hot stream, inlet of the cold stream, outlet of the cold stream. After putting the values in this formula, you can get the value of delta T Lm. So for different configurations, you have to use the value of F as well. To determine the value of F, first you have to get the values of P and R. For the values of P and R, you need to have the four temperatures, right? The inlet temperature and the outlet temperature of the hot stream, and the inlet and the outlet of the cold stream. After putting the value of these four temperatures into these two formulas, you will get the value of P and R. And after that, you have to go for a particular figure, which I will show you in the upcoming slide, to get the value of particular correction factor. So this is the temperature ratio, which is represented by capital R, can also be determined by using this formula. So this is a figure which is for the one shell pass, and if there are multiple tube passes, either for the 2 tube passes, 4 or 6 and so on, right? So this is the configuration, which is the one shell pass and the 2 tube passes. For example, if you have the four temperatures, right, inlet and outlet of hot stream and inlet and outlet of cold stream, and you have the value of P, right, and if you have the value of P 0.5, so and the value of R is 1, what you will do is you will start from the value of P 0.5 and you will go up, right? When this vertical line intersects at the value of the R, which is equal to 1, so you will put 1 point over here, and then you will draw the horizontal line, and then ultimately on the y-axis you will get the value of the correction factor, which will be equal to 0.8, right? So you will get at the end the value of correction factor, which will be equal to 0.8. This is only for the case when the value of the P is 0.5 and the R is 1. So you will get any value, or you can get any value from 0 to 1 in case of P, and for the R you can have any values from 0.2 to 4 for this geometry, that one shell pass and the multiple tube passes. Similarly, this is the second table which is at the bottom, and this table can be used for 2 shell passes and the 2 passes which are multiple of 4. So it means that 4, 8, 12 and so on, you have to use this table. So this is the configuration which is mentioned over here, that the 2 tube passes, this is the first tube pass, this is the second tube pass, and there are 4 tube there are 2 shell passes, right? This is the first shell pass, this is the second shell pass, and 4 tube passes, right? This is first, this is second, this is third, and this is 4. So that's why this configuration is 2 shell passes and the multiple of 4 tube passes. So by using different configurations, you can have the value of the correction factor, and you have to use that correction factor and multiply it with the delta T Lm, which is the log mean temperature difference. So why we are doing this, I am repeating this once again, that we have determined the value of log mean temperature difference only for the double pipe configuration. If we have different configurations or different shell passes or different tube passes, we have to use the correction factor F with the value of log mean temperature difference in order to use, or in order to get the true value of Lmtd. Similarly, these are the graphs for single pass cross flow with both fluids unmixed, right? So this is a one kind of geometry, and similarly the lower graph, which is the single pass cross flow with one fluid is mixed and the other fluid is unmixed. So for different configurations you have different graphs, and these graphs are given, and in your book you can have a look as well on and for different configuration you can get the value of the correction factor. So the Lmtd method is very suitable for determining the size of the heat exchanger to realize the prescribed outlet temperatures when the mass flow rates and the inlet and the outlet temperatures of the hot and the cold fluids are specified. So one thing that you need to keep in mind, that so Lmtd method is useful to determine the size of the heat exchanger. I will bring 1 or 2 examples at the end of this lecture so that you will get the idea about how to use this Lmtd method to determine the size of the heat exchanger. So you have to use this method when you have to determine the size or the surface area, which was represented by AS, provided that you are either given with all the 4 temperatures of 2 temperatures for the hot stream and the 2 temperatures for the cold stream, as well as the mass flow rate. So how to use this Lmtd method? There are few steps that you have to follow to determine the size of the particular heat exchanger using this Lmtd method. So with Lmtd method, the task is to select a heat exchanger that will meet the prescribed heat transfer requirements. So the procedure to be followed by the selection process is, first of all, you have to select the type of the heat exchanger that is suitable for the particular application that you have to use, right? And the second is determine any unknown inlet or the outlet temperature and the heat transfer rate using the energy balance. First is the selection of the heat exchanger for that particular application. Second step is to determine either the unknown temperatures or the heat transfer rate using the energy balance. So I have already explained the energy balance in the previous slides, you can have a look as well. So the second step is to apply the energy balance to determine the unknown inlet or outlet temperatures and the heat transfer rate. Third is to calculate the log mean temperature difference, that is delta T Lm, right? And you have to determine the correction factor as well, because Lmtd is determined only for the simplified geometry, and for different configurations, or for multi shell pass or multi tube passes, you have to use, or you have to determine the value of the correction factor as well. So the third step is determine the log mean temperature difference and the correction factor. And the fourth step is obtain or select or calculate the value of the overall heat transfer coefficient. Sometimes you have to determine the overall heat transfer coefficient. Sometimes it is given in the literature, or when I talk about the exams, maybe I will provide you the particular value of the heat exchanger in order to minimize the length of the question that I will ask in the exam. Anyhow, I will bring one example in the problem set that will explain about the use of, or to calculate, how to calculate the overall heat transfer coefficient, so that you will get the idea. So the final step is you have to determine the heat transfer surface area, and from the surface area you will get that you will get the idea that how big or how small will be the heat exchanger. So the task is completed by selecting a heat exchanger that has a heat transfer surface area equal to or larger than the AS. So once you have the value of AS, you will select a particular heat exchanger which will meet your requirements. So all these steps are applied on this formula that I have already shown you over here, right? So this is the heat transfer rate, which is determined by the energy balance, and this is the overall heat transfer coefficient, which either you have to calculate or you have to determine, and this is the log mean temperature difference. You can calculate the log mean temperature difference value by putting all the values, 4 temperature values in this formula, and then you have to calculate the correction factor as well, and you have all the values except the surface area. So you will keep the surface area on the right hand side, and remaining all the variables are taken to the left hand side, right? And in this way you will have the value of the surface area. From this surface area you can choose a particular heat exchanger for your particular application. So let's have a look on this topic which is called the effectiveness Ntu method. Second kind of problem that encountered in the heat exchanger analysis is the determination of the heat transfer rate and the outlet temperatures of the hot and the cold fluids for the prescribed or the given fluid mass flow rates and the inlet temperatures when the type as well as the size of the heat exchangers are specified. So the heat transfer surface area A of the heat exchanger in this case is known. So what is not given in the previous method, you had to determine the surface area, right, which was represented by A. So in this case you are given with the size or the surface area, but what things are missing? The missing is the outlet temperatures, right? So the outlet temperatures or the heat transfer rates are not given, so you have to determine the outlet temperatures. For example, the inlet temperature, right? So in this case the inlet temperature, the hot fluid inlet temperatures are given, right? And the cold fluid inlet temperature and is given. So what is not given? So you are not given with the outlet temperatures, right? So the outlet temperatures are not given, so you have to determine the outlet temperature in this case. The task is to determine the heat transfer performance of a specified heat exchanger. Why we say the specified heat exchanger? Because the surface area is already given, and to determine if the heat exchanger is available in storage will do the particular kind of job for that particular application, right? So in this case, for example, let's say we have a particular heat exchanger in our storage. So we will see that whether we can use that heat exchanger which is available in our inventory or not. So the Lmtd method could still be used for this alternative problem, but the procedure would require so many iterations and that would not be practical. So in an attempt to eliminate this multiple iteration and from the solution of such kind of problems, so Case and Linden came up with a method in 1955 called the effectiveness Ntu method, which greatly simplified the heat exchanger analysis. This method is basically based on the dimensionless parameter which is called the heat transfer effectiveness, which is represented by epsilon, and it is the ratio of Q dot over Q max. right? So what is Q dot is the actual heat transfer rate divided by the maximum possible heat transfer rate, right? So for a given situation, you have to determine the maximum possible heat transfer rate for the given situation and the actual heat transfer rate. After putting the values, you can have a look on that, the effectiveness, right, or this dimensionless parameter, the effectiveness, which is represented by epsilon. So the actual heat transfer rate in the heat exchanger can be determined from an energy balance that we have already performed in the previous slides, and this energy balance for the hot and the cold fluids can be expressed by these formulas, right? This is the heat transfer rate for the cold fluid is equal to the heat capacity rate multiplied by the temperature difference in the cold fluid, right, is equal to or the heat transfer rate is equal to the heat capacity rate for the hot fluid and the multiplied by the temperature difference in the hot fluid stream. So previously we had said that this heat capacity rate is the product of mass flow rate multiplied by the specific heat for the cold fluid stream, as well as the heat capacity rate for the hot fluid stream is equal to the mass flow rate multiplied by the specific heat for the hot fluid, right? So these are the formulas that we have already discussed in the previous slides. To determine the maximum possible rate in a particular heat exchanger, first we have to recognize that the maximum temperature difference in the heat exchanger is the difference between the inlet temperature of the hot stream and the cold fluid stream. So when you have the heat exchanger, right, so for example, this simplified is heat exchanger is this double pipe heat exchanger. So the maximum temperature change would only be possible, and we can say that by using this formula, that the hot inlet temperature of the hot stream, right, and the inlet of the cold stream. When we take the difference between these two values, we have the maximum value of delta T, right? If we have the maximum value of delta T, what will we see? That we will have the maximum value of the heat transfer rate. So initially we just said that this is the effectiveness Ntu method, and this is particularly used when we don't have the outlet temperatures, right, and we don't have the heat transfer rate. So first of all, we have just defined this, the effectiveness ratio, heat transfer effectiveness ratio, which is the ratio of actual heat transfer rate and the maximum possible heat transfer rate. So first we have to determine this ratio. In order to determine this ratio, first we have to determine Q max and then Q dot. Q max is the maximum possible heat transfer rate and the Q dot is the actual heat transfer rate. And we are now going for the determination of the Q max. Q max is the maximum possible heat transfer rate, and the maximum possible heat transfer rate is only possible when we have the maximum value of delta T. And the maximum value of delta T is only possible when we take the difference between the inlet temperature of the hot stream and the inlet temperature of the cold stream. So when we take the difference between these two temperatures, right, inlet temperature of the hot stream and the inlet temperature of the cold stream, when we take the difference, so we will have the maximum value of delta T, right, which is simply represented by delta T max. So the heat transfer in a heat exchanger will reach its maximum value only for the two cases. Number one, the cold fluid is heated to the inlet temperature of the hot fluid. This is the first case. Second case is the hot fluid is cooled to the inlet temperature of the cold fluid. So these are the two possible cases for which we can have the maximum value of the heat transfer. So I have just explained the two limits, that how we can reach the maximum value of the heat transfer, right? So these two limits cannot be reached simultaneously until or unless the heat capacity rates of both the fluids, such as the hot and the cold fluids, are identical. So usually the heat capacity rates for both of the fluids are not same in the actual case. It is only possible the heat transfer rates are same when we are using the same fluids on the both sides. So in the real problems or in the industry, we usually have different fluids for the hot stream and for the cold stream. So the heat capacity rates for the hot fluid as well as for the cold fluid are usually different, right? So when the heat capacity rate for the hot fluid and the cold fluids are different, so here I am just giving you one important line, that the maximum possible heat transfer rate is only possible when we have the heat capacity rate and or we have the smallest value of the heat capacity rate. And I will just explain it with this value, with this example. That for example, this is a double pipe heat exchanger. This is the hot oil which is entering in the inner pipe at the temperature of 130 degrees centigrade, and the mass flow rate is 40 kilogram per second, and the specific heat is 2.3 kilojoule per kg per Kelvin, right? Similarly, this is the cold fluid which is entering at 20 degrees centigrade with a mass flow rate of 25 kilogram per second, as well as the specific heat which is 4.18 kilojoule per kg per Kelvin, right? So first we have to determine the heat capacity rate for the cold fluid. So this is the formula for the heat capacity rate, Cc, the heat capacity rate for the cold fluid, which is the product of the mass flow rate multiplied by the heat capacity. So we will have the heat capacity rate for the cold fluid, which is 104.5 kilowatt per Kelvin. And similarly for the hot fluid, we can have the heat capacity rate by multiplying its mass flow rate, right, which is 40 multiplied by Cph, which is 2.3. We can have the value of the heat capacity rate, which is 92. So the maximum heat transfer rate would, or the maximum heat transfer would only be possible if we use this value, which is the smaller value, right? And the smaller value is actually represented by C min, right? So keep in mind that the ultimate objective, we have to determine the value of Q max. So Q max would only be possible when we have the maximum value of delta T, right, and the minimum value of C min, right? Or C min is the minimum value of the heat capacity rate. So when we have the heat exchanger, we have the values for the hot fluid stream and we have the inlet value of the cold fluid stream. So we determine the heat capacity rate for the cold fluid, we determine the heat capacity rate for the hot fluid. So the heat capacity rate, which is smaller, right, and this is 92, we will use this value as our C min, and C min is the decisive parameter which will give us the maximum possible heat transfer rate, right? So the fluid with a smaller heat capacity rate will experience a large temperature change. So we are discussing the large temperature change. So it will be the first to experience the maximum temperature change. So the question is, why we are using this smaller value? So I have just said earlier that the heat capacity rate, which has the smaller value, because it will experience the large temperature change, and the heat capacity rate is the heat capacity rate which will experience first the maximum temperature change, or the maximum temperature at which point the heat transfer rate will become stopped or will become finished. So at this point you have to use this value, which is the value of C min, for the determination of Q max. So our ultimate objective is to determine the effectiveness ratio or the heat transfer effectiveness. For the heat transfer effectiveness, we have Q or we have the Q max. How we can determine the Q max? It is very simple, that we have the inlet of the cold stream, we have the inlet of the hot stream. We just perform these calculations, right? And after that we can simply get the values of the Q max. So the determination of Q max, which requires the availability of the inlet temperature of the hot and the cold fluids and their mass flow rates, which I have already explained in the previous slides. which are usually specified in the previous example or previous slide as well. Then once we have the effectiveness of the heat exchanger is unknown, or we know the value of the effectiveness epsilon, we can get the value of the actual heat transfer rate by using this formula, right? So this is the same formula that has been modified from this formula, right? So we have the maximum heat transfer rate, we multiply it with the epsilon, which is the effectiveness, we will get the value of, or we will get the formula of actual heat transfer rate is the product of effectiveness and the Q max, right? So we have just determined the formula for the Q max in the previous slide, which is C min multiplied by the delta T max, which is the maximum temperature change, and maximum temperature change is the difference between the inlet of the hot fluid stream minus the inlet of the cold fluid stream. So by using this formula, right, we can have the value of the actual heat transfer rate, right? So the question is how we can get the value of this epsilon, right? We can have the value of Q max, right, once we are given with the inlet temperature of the hot, inlet temperature of the cold fluid stream, and the mass flow rate, and the specific heats are given, we can have the value of Q max. Now the question is how we can get the value of epsilon. So I will explain it in the upcoming slide that there are different techniques, or the value of the effectiveness is actually dependent on the geometries, right? So I will explain it in the upcoming slide. So here I will first explain this diagram, that the hot fluid is entering in the inner pipe and the cold fluid is entering over here. The mass flow rate of the hot fluid is m dot h and the specific heat is the Cph, and similarly this is the mass flow rate and the specific heat for the cold fluid. So the temperature rise of the cold fluid in the heat exchanger will be equal to the temperature drop of the hot fluid when the heat capacity rates, right? So the product of these two is the heat capacity rate. When the heat capacity rate of the hot fluid and the cold fluid are identical. When the heat capacity rates are identical, what does it mean? The temperature increase in the cold fluid in the heat exchanger will equal to the temperature decrease in the hot fluid stream in the heat exchanger, right? So this is actually the trade-off. So the amount of the degree of the temperature that decreases in the hot fluid stream will be equal to the temperature increase in the cold fluid stream in the heat exchanger, right? So in the previous slide that we have said that the CH was the C min value, but it is not always the case. So it depends upon the inlet temperature as well as the specific heat. So if the value of the cold fluid heat capacity rate is minimum, right, so which is C minimum, the value of the effectiveness would be determined by using this formula, right? So in this case C are same, so it will be cancelled out, we will have this formula, right? So as in the previous slide, we have the value of the hot fluid heat capacity rate minimum. So we said that the C minimum value is the heat capacity rate for the hot fluid. For that case, the effectiveness is can be written as in this way by using this formula. So CH would be same, so it will be cancelled out, it will be the ratio of these four temperatures, right? The hot fluid temperature, outlet hot fluid temperature, and this is actually a misprint that here this must be TH in instead of TH out, right? So as it is mentioned over here. So these are the two formulas for the effectiveness. So from the values of the inlet temperature of the hot stream and the cold stream and the mass flow rates and their specific heats, we can have the value of the C min, right? Whichever the value of the heat capacity rate is the minimum, we can then define the value of the C min and then use the particular formula for the determination of the effectiveness. So here is the derivation that I have already said in the previous slide, that the effectiveness of the heat exchanger actually depends upon the geometry as well as the flow arrangement, right? So there are different kinds of geometries and there are different kinds of flow arrangements, so that's why we have to use different value for the effectiveness for different geometry and for different flow arrangement. So therefore different types of the heat exchangers have different effectiveness relations. So here for the parallel flow, right, and the double pipe heat exchanger geometry, so this is the final expression for the effectiveness, right? So this is the final expression. So no need to go through this derivation. I will not ask about the derivation in the exam, but you have to go through it, how this derivation is carried out. It is simply very straightforward, and you can have book as well. Ultimately you have to look at this formula. So in this formula nothing is new, everything is already known. That for example, U is the overall heat transfer coefficient, AS is the surface area, C min is the minimum heat capacity rate, and C max is the maximum heat capacity rate. So everything in this formula is given, so nothing is new. So in the upcoming slide I will also explain about the effectiveness relation of the heat exchanger. Typically involves a dimensionless group, which is known as the number of transfer units, and this ratio, which is represented over here, UAS over C min, right? This is the ratio which can be simply represented by NTU. The full form of the NTU is the number of transfer units. So I have explained the importance of the number of transfer units in one of the previous lectures. You might have idea that what is the NTU, which is the effectiveness, which tells us that how effective the heat will be transferred for that particular situation, right? So for the specified values of the overall heat transfer coefficient and the C min value, you can have the value of the NTU, which is the measure of the surface area, right? So if you specify the value of C min and the overall heat transfer coefficient, so ultimately there will be the direct relationship between the NTU and the heat transfer surface area. So larger the value of this NTU, what does it mean? Larger will be the heat exchanger surface area, right? So in the previous formula, in this formula we have just said that the ratio of these two, in this formula this ratio is known as the number of transfer units, right? So we are also going to introduce a new parameter, and the ratio of C min over C max, right? So we are just saying that the smaller c is equal to the ratio of C min over C max, which is known as the capacity ratio, right? And ultimately we have all these terms, right? This is the NTU, this is the capacity ratio, this is also the capacity ratio. So what we say that the effectiveness is actually the function of the number of transfer units as well as the capacity ratio, which is represented by smaller c. So here the effectiveness of a heat exchanger is a function of the number of transfer units NTU and the capacity ratio C, and it can simply be represented by this form, right? So this is the smallest elaborative form, which says that the effectiveness of a heat exchanger is the function of the number of transfer units, which is the ratio of overall heat transfer coefficient surface area C min and the capacity ratio, which is actually a ratio of the minimum heat capacity rate and the maximum heat capacity rate. So this is the table which will give you the different formulas for, or the different relationships for the effectiveness of heat exchangers for different configurations, right? For example, this is the double pipe parallel flow arrangement. You have just seen the value of the effectiveness in the previous slide. So this is the expression for the counterflow. And similarly, for the shell and tube heat exchanger, one shell pass and the multiple of two shell tube passes, we can have the value of the effectiveness, the relationship for the effectiveness here, right? So this is the table which shows different relationships for the effectiveness of the heat exchanger depending upon their geometries. So the effectiveness of the heat exchangers, right, the value of the epsilon, right, so it can be determined for different geometries if we know the value of the NTU, right, the number of transfer units. What is the number of transfer units? So if we have the surface area, overall heat transfer coefficient, and the minimum heat capacity rate, C min, right? So at the start of this topic, I have just said that in this type of problem, we have known values, and which is the heat transfer surface area, and what is missing, what was missing. So the missing was the outlet temperatures, right? So the effectiveness Ntu method, we are given with the heat transfer surface area, right? So for the double pipe heat exchanger with the parallel flow, if we have the Ntu, the number of transfer units, right? For example, it is 3, and the heat capacity ratio is actually 1. So what we will do is we will put our pointer over here, and we will go upward, or vertical line. We'll draw the vertical line until it will intersect with the the capacity ratio line, which we already said that is equal to 1. So we will put our pointer over here, and then we will draw the horizontal line. So the effectiveness would be the 50%. So similarly, so you can have the value of the effectiveness for the double pipe heat exchanger for the counter current flow, and similarly this is one shell pass, 2 tube passes, or the multiple of 2 tube passes, right? This is for the 2 shell passes and the 4 tube passes, or the multiple of 4 tube passes, right? 4, 8, 12, 16, and so on. Similarly, you can have the value of the effectiveness for the cross flow geometry with both fluids are unmixed. And similarly, what you have to do is you need to determine the value of NTU right over here, and then the capacity ratio, right? So you will draw the vertical line over here. Whatever the capacity ratio you have, for example 0.5, you will go over here, and then you will draw the horizontal line. You will get the effectiveness of that particular heat exchanger. Similarly, this is the graph for the effectiveness for the cross flow configuration with one fluid is mixed and the other fluid is unmixed. So this is the table which shows the relationship of the NTU in terms of the effectiveness and the capacity ratio, right, for different kind of geometries. So here is an important description that I will explain, that when all the inlet and outlet temperatures are specified and the size of the heat exchanger can easily be determined using the Lntd method. So this is the first method that I have already explained in the previous topic, that all the inlet and the outlet temperatures and the mass flow rates are given. You have just to determine the size, which is the surface area AS, by using the Lntd method. Alternatively, it can be determined, which is actually the size, right, from the effectiveness Ntu method, first by evaluating the effectiveness from its definition, right, and then the Ntu from the appropriate Ntu relation, right. So because in the previous slide I have said that the Ntu is particularly related with the surface area, right. So here I have said that the larger the NTU, the larger the heat exchanger, or the larger the surface area. So in this last line, it is said that first you have to determine the effectiveness NTU method by first evaluating the effectiveness from its definition, right? So from the definition or from these graphs, we can determine the value of the effectiveness, and if we have the value of the effectiveness, right, and if we have the value of the capacity ratio, we can get the value of NTU, and from the value of the NTU, we can just evaluate the size of the heat exchanger, right? So I will explain these two graphs a little bit later. First, let me just read the few observations that we have made after reading the graphs in the previous slide, right? So the value of the effectiveness ranges from 0 to 1, right? So effectiveness, the value of the effectiveness from ranges 0 to 1. So it means that percent, when we divide it by 100, so it will be from 0 to 1. So the effectiveness value ranges from 0 to 1. So the effectiveness rapidly increases with NTU for small values, or up to the NTU value 1.5. So what does it mean? That when you increase the value of NTU from 0, 0.1, 0.2, 0.3, 0.4 up to the value of NTU, that is 1.5, the effectiveness increases rapidly, but rather slowly for the large values. Let me just show you over here. So this is the NTU, right? If the NTU is changing in this region, right, in this region from 0 to 1.5, the effectiveness, the change in the effectiveness is very rapid, or the effectiveness changes very rapidly. If the NTU is in between the range of 0 to 1.5, if the NTU is changing from 3 to 4, what does it mean? The effectiveness is changing very slowly, right? The effectiveness changed, or the change in the effectiveness is very small, right? Let me just rephrase it once again. If the effectiveness changes from, or the NTU value is changing from 0 to 1.5, the change in the effectiveness is very high, or the very rapid change. Secondly, if the value of the NTU is changing from 3 to 4, or the higher value, what does it mean? The change in the effectiveness is very small. Therefore, the use of the heat exchanger with the large NTU, usually larger than 3, and thus a large size, cannot be justified economically, since the large increase in the NTU in this case correspond to the small increase in the effectiveness. So when we are above the value of the 3 of the NTU value, so there will be very small change in the effectiveness, right? So rather we keep our size of the heat exchanger on the lower side, because NTU is related with the size of the heat exchanger as well when you specify the overall heat transfer coefficient and the minimum heat capacity rate. So the next is, for a given NTU value, this is the important point that I will explain the two graphs, these two graphs, with the help of the second point. So for a given NTU value and the capacity ratio value, the counter flow heat exchanger has the highest effectiveness, and then followed closely by the cross flow heat exchanger with both fluids unmixed, and then the lowest effectiveness values are encountered in the parallel flow heat exchanger. So this point is saying that if you have the fixed value of NTU and the fixed value of capacity ratio, then we are comparing the different configurations, right, of the flow arrangements. So the maximum heat, the effectiveness would be for the counter current flow. So this is the case, right? So if we specify the value of the NTU, which is 3, right, and this is the 3 graphs for the capacity ratio is 1, right? So at the value of 3 of NTU, the maximum effectiveness would be for the counter current flow, and then again followed by the cross flow arrangement of the fluid with both unfluid, with both of the fluids are unmixed, and the minimum value of the effectiveness is for the parallel flow arrangements. The third point is the effectiveness of a heat exchanger is independent to the capacity ratio C for the NTU values less than 0.3. So right, this is the case over here. So when the value of the NTU is less than 0.3, so we cannot distinguish between the different capacity ratios, right? So here in the third point it is saying that when the NTU value is less than 0.3, so this capacity ratio effect is independent, so we cannot distinguish between the different lines of the capacity ratio, so it all becomes a one line. So for the value of the NTU which is less than 0.3, we cannot distinguish, or we cannot differentiate between the different lines of the capacity ratio. So what the third point is saying, that the effectiveness of the heat exchanger is independent of the capacity ratio C for the NTU values less than 0.3. And the last point is the value of the heat capacity ratio C ranges from always 0 to 1. So these are the graphs. So the heat capacity ratio values changing from 0 to 1, right, for all the graphs that I have mentioned in the previous slides. For a given NTU value, the effectiveness becomes maximum for the value of the capacity ratio would become equal to 0. This is only the case for the boiler as well as for the condenser. When the capacity ratio would be the minimum, and the value of the NTU would be minimum when for the value of C is equal to 1. This is usually the case when the heat capacity rates of the two fluids are equal. So this is the last topic, which is known as the selection of the heat exchanger. So it depends upon many parameters, right? The heat transfer, enhancement, and the heat exchanger is usually accompanied by the increase in pressure drop and the higher pumping power. We have to incorporate different parameters when we select the particular heat exchanger. So there are different selecting parameters on which we select a particular heat exchanger. The parameters include the heat transfer rate, cost, and the pumping power, and the size, and the weight, and the type, and the materials of construction of the heat exchanger. So I have already explained all these points in very detail in one of the previous lectures. You can go through that particular lecture. So I will explain now about the different problems related to the NTU method, NTU effectiveness method, and the Lmtd method, so that you will get the idea that after reading the theory, how we can put this into solving a problem, right, for the Lmtd method as well as for the effectiveness NTU method. So let's have a look on this problem, which is the heating water in a counterflow heat exchanger. Let me just read the question statement first, that the counterflow double pipe heat exchanger is to heat the water from 20 degrees centigrade to 80 degrees centigrade at the rate of 1.2 kilogram per second. This is the mass flow rate, right? We have this the cold water, which is initially at present 20 degrees centigrade, and we have to heat up this cold water up to 80 degrees centigrade, and the mass flow rate of the cold water is 1.2 kilogram per second. The heating is to be accomplished by the geothermal water available. So we have another stream of the hot water, right, which is available at the 160 degrees centigrade with the mass flow rate of 2 kilogram per second. And the inner tube is thin walled of the double pipe heat exchanger and has a diameter of 1.5 centimeter. If the overall heat transfer coefficient of the heat exchanger is given, right, which is given over here 640 watt per meter square per degree centigrade. So determine the length of the heat exchanger required to achieve the desired heating. So what you are given is, you are given with the inlet temperature of and the outlet temperature of the cold fluid and the mass flow rate of the cold fluid as well. So you are given with the mass flow rate of the hot fluid and as well as the inlet temperature of the hot fluid. So ultimately you are given the three temperatures. The outlet of the hot fluid stream is not given, or the outlet temperature of the hot fluid stream is not given. You have to determine this, the outlet temperature of the hot fluid stream, or simply the fourth temperature, right? So you are given with the two mass flow rate of the hot fluid and the cold fluid as well, and you are given with the inner diameter of the inner pipe, right? Let me just go to the solution, that the water is heated in the counterflow double pipe heat exchanger by the geothermal water. So the required length of the heat exchanger is to be determined. That we take some assumptions So the steady operating conditions exist. Number two, the heat exchanger is well insulated, that the heat loss to the surrounding is negligible, and the heat transfer from the hot fluid is equal to the heat transfer to the cold fluid. These are the few assumptions, basic assumptions that you have to take every time. That if you don't take these assumptions, that there might be some complications, that you will not be able to solve the problem easily, right, if you don't take these assumptions. So changes in the kinetic and the potential energies of the fluid streams are negligible. And the fourth is there is no fouling, but in the actual case there is fouling, but in this problem we are neglecting the presence of fouling. So the fluid properties are constant. So what other properties that we need is, so take the specific heat of the water as well as the fluid, the geothermal fluid. Simply we have to determine the specific heats for the cold fluid, which is simply water, and the hot fluid, which is given is as geothermal fluid. So the specific heat for the cold fluid is 4.18, and the specific heat for the hot fluid is 4.131 kilojoule per kg per degree centigrade. So let me just perform the analysis. That the schematics of the heat exchanger is given in the previous diagram, that the rate of the heat exchanger can be determined by using this formula, that how much heat is being taken up by the cold fluid, right? So this is the simplest formula that we can put for the cold fluid stream, right? Why we put this formula for the cold fluid stream? Because we are only given with the two temperatures of the cold fluid stream, right? So we are given with the mass flow rate, we are given with the specific heat, right, that we have determined, or we have taken from the literature, that is 4.18, and the inlet and the outlet temperature of the cold fluid streams are also given. So after putting the value, that the total heat transfer rate or the amount of heat which is taken up by the cold fluid is 301 kilowatt. So noting that all of this is the heat which is supplied by, this is the amount of heat which is supplied by the hot fluid, right? So similarly we apply this the similar formula for the hot fluid, right? For the hot fluid we apply the heat transfer rate and the mass flow rate and the specific heat, inlet temperature and the outlet temperature. So everything is given, right? So the outlet temperature is not given, right? Inlet temperature of the hot fluid stream is given, the heat specific heat we taken from the literature, mass flow rate is given in the question statement. So this Q would be the same that we have determined here for the cold fluid. So this is the amount of heat, this is the amount of heat which is taken up by the cold fluid, and in opposite we can say that this is the amount of heat which is provided by the hot fluid. So we will just put 301 kilowatt over here, and after simplifying that we will have the value of the outlet temperature of the hot fluid stream, which is 125 degrees centigrade. After that, for the for getting four different temperatures, the inlet and the outlet of the cold stream, we have these two temperatures, and we have the inlet and the outlet of the hot fluid stream we are given, and we have just calculated this 125 degrees centigrade, which is the outlet of the hot fluid stream temperature. So we have then to determine the log mean temperature difference for the counter current flow. So the formula is given, so you can memorize this formula either for the counter current flow or the parallel flow. After putting that, this is the LMTD, or the log mean temperature difference, which is simply the average temperature, and you, after having this value, you will have to put this value over here in this formula. This is the famous formula to determine the heat transfer rate. From this we have given with this Q value that we have just determined in the previous slide, that is 301 kilowatt, and the overall heat transfer coefficient is also given in the question statement, and the LMTD that we have just determined over here, right, that is 92 degrees centigrade. And after we are not given with the surface area, so we'll take the surface area on one hand side and remaining all the parameters on the other hand side, and after putting that we will get the value of the surface area, which is 5.11 meter square, right? And this is actually the Lmtd method, right? So you have to use the log mean temperature difference, and you have to determine the surface area. and ultimately you are given with the diameter, and you have to determine the length of the heat exchanger. So the surface area of the heat exchanger would be equal to pi dl. So the surface area is given, the value of pi is non-value, and the diameter is also given in the question statement. That was 1.5 centimeter, and if you convert it into meters, that will be equal to 0.015 meters. So you have to determine the length of the heat exchanger. So you will keep the length of the heat exchanger on one hand side, and remaining all the other parameters on the right hand side, you will get the value of the length of the heat exchanger, which will be equal to 108 meter, which is the length of the heat exchanger. So let's have a look the same problem that that I have explained in the previous slides, that we have the counter current flow heat exchanger, that the inlet of the cold fluid temperature, inlet of the cold fluid stream is at 20 degrees centigrade and the outlet is 80 degrees centigrade, and the inlet of the hot fluid stream is at 160 degrees centigrade and the outlet temperature is not given, and the inlet the mass flow rate of the cold fluid stream is 1.2 and the kilogram per second, and the mass flow rate of the hot fluid stream is 2 kilogram per second, and similarly the overall heat transfer coefficient is 640 watt per meter square per degree centigrade, right? So this is the same problem statement that you have to solve this problem using effectiveness Ntu method. So this is the same problem that you have to determine the overall the length of the heat exchanger required to achieve the particular or the desired heating. So let's have a look on the solution. The solution is the schematics of the heat exchanger is already explained in the previous slide. So the assumptions are same that I have already explained in the previous example or the previous problem. Let's have a look on the analysis. In the effectiveness Ntu method, first we determine the heat capacity rates for the hot fluid stream and the cold fluid streams and identify the smaller one, right? So how can we determine the heat capacity rate, right? So for the heat capacity rate of the hot fluid, we just multiply the mass flow rate and the specific heats, right? So after multiplying it, we will get the value of the heat capacity rate, which is 8.62 kilowatt per degree centigrade. Similarly, the heat capacity rate for the cold fluid is the multiplication of the mass flow rate and the specific heat, and after multiplying the values, you will get the value of 5.02 kilowatt per degree centigrade, right? So we have to identify that which of the heat capacity rate is the smaller one. Obviously, when we compare these two values, we will have a look on this value, that is 5.02, which is the smaller one. So the heat capacity rate for the cold fluid would be our C min value. So keep in mind that this C min value is very important. We will be going to use this value in the upcoming slide formulas. So the second thing is we have to determine the capacity ratio. What is the capacity ratio? I have already explained in the previous slide that the ratio of the C min or the C max and the C max. And after putting the values of C min, which is 5.02, and the C max is 8.62, we will have the capacity ratio, which is 0.583. Now the next thing is we have to determine the maximum heat transfer rate, right? So the maximum heat transfer rate formula is Q max, right, is equal to C min that we have determined in the previous slide, and the delta T max, and the delta T max is the hot fluid inlet and the cold fluid inlet, right? So we are given with the hot fluid inlet, which is 160 degrees centigrade, and the cold fluid inlet, which is 20 degrees centigrade, and after putting all the values, this would be the maximum possible heat transfer rate in the heat exchanger, which is 702.8 kilowatt, right? So we have the value of the Q max. Now we are going to determine the value of Q dot, which is the actual heat transfer rate. So let me just read the once again that the effectiveness is represented by epsilon. It is the ratio of actual heat transfer rate divided by the maximum possible heat transfer rate. So we have just determined the maximum possible heat transfer rate, which is Q max, which is 702.8 kilowatt. Now we have to determine the actual heat transfer rate in the heat exchanger. That is the same formula that used in the previous slide. So after putting all the values, you have just determined the actual heat transfer rate between the two fluids, that is 301.0 kilowatt, right? So what is the effectiveness of the heat exchanger? It is the ratio of the actual heat transfer rate divided by the Q max, or the maximum possible heat transfer rate. So this is Q dot or Q dot max divided by Q dot max. After putting the values, that is the actual heat transfer rate 301.0 kilowatt divided by 702.8 kilowatt, which is the maximum possible heat transfer rate. So after dividing this, you have the effectiveness value or the epsilon value, which is 0.428, which is the effectiveness, right? So keep in mind that our goal is to determine the length of the heat exchanger. So previously we have adopted a different route. Now this time we have adopted the effectiveness Ntu method route in order to determine the length of the heat exchanger. So the next is we have to use the formula for the Ntu number of transfer unit formula for the counter flow heat exchanger, and it can be taken from the table which I have mentioned in the slide, one of the slide in the lecture. So this is the formula for the Ntu number of transfer unit for the counter flow heat exchanger, right? So in this formula everything is given, right? The C, which is the capacity ratio, we have determined in the previous slide, and the effectiveness we have also determined in the previous slide, and nothing new in this formula. So after putting the values of the capacity ratio and the effectiveness, and ultimately we will get the value of the Ntu, which is 0.615, right? So this is the Ntu, which is the number of transfer units. We also know that the number of transfer units is the ratio of U, which is the overall heat transfer coefficient, AS is the surface area, divided by C min. So after rearranging it, so we will get the surface area on one hand side, number of transfer units, C min, and the overall heat transfer coefficient. So let's have a look on this. Number of transfer unit is there. Yes, we have the value of the number of transfer units, which is 0.651, and C min that we have calculated in the previous slide, and U, which is the overall heat transfer coefficient, which is also given in the question statement, right? And after putting all the values of Ntu, C min, and the U overall heat transfer coefficient, we will have the same surface area, that is 5.1. And after opening the surface area formula, which will be equal to pi dl, we will separate the length of the heat exchanger on one hand side and remaining all the parameters on the other hand side, because we are given with the diameter of the heat exchanger of the inner pipe, right? And after putting the value, we will get the length of the heat exchanger, which is 108 meter. So we have obtained the same results that we determined in the previous example. So whichever the route you have adopted, the ultimate result would be the same. So previously we have adopted the route of determining the length of the heat exchanger using the Lmtd method, and this time we have adopted the route of determining the length of the heat exchanger for that is the route is the effectiveness Ntu method, and the ultimate result is same, which is the length of the heat exchanger equal to 108 meter. So the next I will explain two small topics, that is the pressure drop in the heat exchanger. This is one of the interesting topic that you will encounter in the upcoming slide as well, and when we design the double pipe or the shell and tube heat exchanger, this will be the most important topic at the end of the design, because ultimately we will see the pressure drop in the heat exchanger as one of the important criterion for the design of the heat exchanger. So in this small topic, I will just show you different formulas, and I will come up with a small example to determine the pressure drop in the heat exchanger. So for the heat exchanger, we usually involve the tubes as well as the shells and different kinds of fittings. So for the tube side pressure drop and the tube cross sectional, the circular cross sectional tube, we have this formula. So in this formula, this is the friction factor, this is the pressure drop, length of the heat exchanger, the internal diameter, and the density of the fluid, and the viscosity, right? So the friction factor for the fluid, which is for the laminar flow, is connected with this formula, right? So the friction factor ultimately determined or is a function of the Reynolds number. So Reynolds number will decide that whether the flow regime is in the laminar flow or is in the transition flow, or in the turbulent flow. So based on the Reynolds number, we will decide the value of the frictional factor, right? So if the value of the Reynolds number is in between this range, we have to use this formula, and we have to put the value of the Reynolds number, and after putting the Reynolds number we will get the value of frictional factor, and after that we will have to put that value in the upper formula that I have shown you in the previous slide for the determination of the pressure drop. Similarly, if you are given with this range of the Reynolds number, you have to use this formula. No need to memorize any kind of formulas, but you need to understand that for a given situation, for a given geometry, or for a given scenario, you have to use that formula. So keep in mind that no need to memorize any kind of formula. You have to analyze which formula is suitable for particular scenario, right? For this range, you have to use this formula for the friction factor. After determining the friction factor, you have to put the value of the friction factor in this formula to get the value of the pressure drop. So this is an important graph which shows the relationship of the Reynolds number as well as the friction factor, right? And ultimately friction factor leads to the determination of the pressure drop by using this relationship. So if you are in the lower value of the Reynolds number, which shows that for the laminar region, right? So let's suppose if the Reynolds number is 1000, which is 10 raised to the power 3. So you will draw the vertical line over here when it intersects with this line. So then you will draw the horizontal line over here, and ultimately you will get the value of the friction factor, right? So this is for only the circular pipes, right? So this formula, and for the transition region, this is the transition region, and from this line to onward, this is the whole region for the turbulent flow and turbulent regime. Because in most of the industries we encountered the flows which are in the turbulent region. So for different turbulent region, and for different tube drawings, or for different geometries, for different materials, we have different values of E, that is divided by the internal diameter of the pipe. So let's suppose if the pipe is made up of the cast iron, you have to use the value of E, that is 0.026, and the internal diameter di, that would be equal to 0.001. and for example, if the Reynolds number value is 10 raised to the power 6, which is in the turbulent region, so for different horizontal line, you will get the value of the particular geometry friction factor. So after getting the value of the friction factor from this graph, you ultimately determine the value of the pressure drop. So here we have the circular pipe. So the pressure, the force balance in this circular pipe is given over here in this formula, which is ultimately related to the shear stress. So this is the previous formula that I have used over here, right? So the pressure, this is the pressure drop. Pressure is, what is pressure? Pressure is the force per unit area. So this is the area of the pipe, right? So this is ultimately the force balance, right? So ultimately this is connected with this friction factor value, which is ultimately related to the wall shear stress. You have to use this friction factor value for a given value of the wall shear stress to determine the value of the friction factor. So the pressure drops may occur in different kinds of other fittings. For example, if two pipes are connected with each other through a fittings, so there might be some contraction, there might be some expansion. If a particular pipe is bended up to certain angle, so there might be some pressure drop. For that pressure drop, you have to use this formula, right, to determine the value of the pressure drop in that particular bend or particular fitting. So here this K stands for the total loss coefficient, and it is further connected with some parameter which is FC, L and DH, which is the hydraulic diameter, and FC is the friction factor in the bends, while this F, simple F, is known as the friction factor for a straight pipe at the Reynolds number in the bend, right? So this K static represents at the end, K static represents the combined loss coefficient other than the friction losses, right? So this friction factor is ultimately connected with the Reynolds number with the given ranges. If the Reynolds number is in between this range, you have to use this formula for the friction factor and then put the value of the friction factor in this formula, and then you will get the value of K, and put the value of K in this formula, you will get the value of this pressure drop, right? So ultimately you have to use this pressure drop value in order to determine the value or the power, the pumping power, right, which is required for the particular heat exchanger, right? So the pumping power would ultimately related to the economics of that particular heat exchanger or economics of this operation. So here is the example that consider the piping circuit of a heat exchanger. In the circuit there are 4 90-degree standard elbows, 3 closed pattern return bands, and 2 check valves, and 2 angle valves, and 3 gate valves, and the valves are fully open. So the straight part of the circuit pipe is 150 meter, and the water at 50 degree centigrade flows with a velocity of 4 meter per second. So you have to the pressure drop in the heat exchanger is also given, which is 12 kilopascal, and the nominal pipe size is 2-inch outer diameter, and the inner diameter is 0.052 meters. So what you have to do is you have to calculate the total pressure drop in the system, right, which has all these elbows and fittings and valves, and calculate the mass flow rate and the pumping power, assuming that the isentropic efficiency of the pump is to be 0.8. So in the previous formula, so there is the pumping power or the pump efficiency, so you have to use that efficiency, which is 0.8, in order to determine the mass flow rate. So here the mass flow rate is given. You have to keep the mass flow rate on one hand side, the pumping power and the density and remaining all the parameters you have to put, and you will get the value of the mass flow rate. So starting with that, you have the pressure drop in the pipe, you are given with this formula, right? So what you have to do is, from the table, which is 4.2, I will explain, or I will leave a message in the group that from which book I have taken this table. I will leave a message in the group so that you can get the idea that I have taken this example from that particular book. So for the pipe and the elbows and the close pattern return bends and the check valves and the angle valves and the gate valves, so the equivalent length divided by the internal diameter ratio is given for these geometries, right? So this will be used in the upcoming slide. That so this information is given, right? So the properties of the water, which usually be determined at the 50 degree centigrade, which is the heat capacity, which is 4181.2 joule per kg per Kelvin, and this is the thermal conductivity and the density and the Prandtl number and the viscosity, right? So these are all the properties of the water which can be taken from the appendix B. The next is you have to determine the Reynolds number, and everything is given that the parameters. After putting in this formula, you will get the value of the Reynolds number, and after seeing the value of the Reynolds number, you will see that this flow is in turbulent region. For the turbulent region, you have to use this formula, right, which is equation number 4 in the chapter number 4, and after putting the value of the Reynolds number, you will get the value of the friction factor, which will be equal to 0.00354, right? And you have to use this friction factor value in the formula of the pressure drop, which was given in the second slide of this topic, right? And everything, after putting everything in this formula, you just leave the value of, or the ratio of, this length to diameter ratio, right? So after putting all the values and leaving this ratio on one hand side, you will get the delta P1, which is the pressure drop in the pipe, right? And you will leave this ratio as it is, which is length over diameter ratio. So this is delta P1. So delta P1 for the minor losses would be calculated for all the fittings, right? So for example, this 90-degree standard elbows, so equivalent length to diameter ratio is 30, right? So there are 4 90-degree standard elbows, so you have to multiply it with the 4, right? So remaining all the other fittings or the valves, the number of valves, you have to multiply the numbers at which they are present, right? So it is mentioned that there are 4 90-degree elbow standard elbows, so you have to multiply it 4 with the 90-degree elbows, and length to diameter ratio is 30. And similarly for all the other parameters, length to diameter ratio is given in the table, and their numbers which is used in the fitting is also mentioned, so you have to put that value. And ultimately for all the minor losses in the gate valves, in the check valves, or in the elbows, you will have the delta P1, which will be equal to 78,225 Pascal. You can convert it into kilopascal after dividing it with the 1000. So the next is for the straight line pipe. So you have to put the value of the length, which is 150, and the diameter which is given over here, which is 0.052, and this will be 322.817 kilopascal, right? So similarly you have to determine the total pressure, right? The total pressure. So the total pressure would be the sum of the minor losses, the sum of the total the pressure in the straight pipe, and the pressure drop in the heat exchanger. And after adding all the values, and you will get the value of the total pressure drop, which is 413.042 kilopascal. And the second part was to determine the pumping power, and the formula was given that after putting all the values, you have to determine, first you have to determine the mass flow rate, right? And after getting the value of the mass flow rate, you have to determine the pumping power, and ultimately putting the values of all the parameters, the mass flow rate and the total pressure drop and the density and the pump efficiency, you will get the pumping power, which is equal to 4.36 kilowatt. The last topic of this lecture is the fouling in the heat exchanger, right? So what is the fouling? Fouling is always defined as the formation and the accumulation of the unwanted materials that deposits on the processing equipment surfaces. So the fouling increases the resistance to flow of the fluid and resulting in the higher pressure drop across the particular heat exchanger. So that's why we have to minimize the fouling in order to minimize the pressure drop, right? So many types of fouling can occur on the heat transfer surfaces. For example, the crystallization fouling and the particulate fouling and the corrosion fouling and the chemical fouling and the biological fouling and the solidification fouling. There are different types of the fouling. So it depends upon the material, or it depends upon the environment, or it depends upon the liquid streams that we are using, and it will cause different kinds of fouling. So the fouling can have a very costly effect in the industries, which eventually increases the fuel usage and ultimately it interrupts the operation of the industry, and production will be decreased, and ultimately it will leads to the increased maintenance cost. So the next is the fouling is formed in 5 different stages, which can be summarized as the initiation of the fouling, and then the fouling particles will be transported to the surface, and then the fouling particles will attach to the surface, and then the removal of the surface, and then aging of the surface. These are the 5 different stages. So there are few parameters that are influencing influence the fouling factors such as the pH of the fluid and the velocity of the fluids, the bulk temperature of the fluids, and the temperature of the heat transfer surface, and the surface structure, and ultimately the roughness of the structure, which ultimately influence the fouling of the particular heat exchanger. So this is a kind of diagram which shows that the deposition and the removal of the fouling, that for example, first of all the sedimentations are formed, and then it will settle down, and then there is the crystallization, the ionization of the particles, and then it will dissolve back in the solution. Then there might be the spalling and the removal of some corrosion particle which will move along the fluid direction, because the flow direction is from left to right. So ultimately the fouling surface will erode away, so the heat transfer will be in this direction, right? So the thickness, the higher the thickness of the fouling layer, so there will be the additional resistance in the direction of the heat transfer. So that's why the fouling should be the minimum in order to maximize the heat transfer rate. So this is a kind of diagram which shows that this is the circular pipe which has the fouling at the inner surfaces. As you can see that there is a thick layer of the deposits at the inner surface of the tube. So ultimately it will reduce the flow area and it will increase the resistance to the heat transfer rate. So the fouling should be minimized in the heat transfer equipments. So another type of unwanted thing is that is known as corrosion. So what is corrosion? The environmental features such as soil, atmosphere, and the water solutions commonly attack the general metals and the alloys. So it will destroy these metals, and the destroying of these metals is simply known as the corrosion, right? So corrosion ultimately affected by several parameters or the several factors. So environment will also impact, and the material properties and the material conditions, right? And ultimately the different stress factors, and all these contribute to different the corrosion process of particular material. So the cost imposed due to the fouling, that apart from the high cost of the heat exchanger fouling, very few work have been reported to accurate determination of the economic penalties caused by the fouling. So a lot of work has been doing around the world, particularly in the oil and gas industry, where extensive piping or extensive metallic work is being utilized. So the fouling is the normal phenomena, or the corrosion is the normal phenomena in the piping industry. So approximately $80 billion around the world has been lost due to the corrosion of the metallic equipment in the industry. Therefore, these attributes the costs to different aspects of the heat exchanger design and the operation. So there are some capital expenditures, and the energy cost, and the maintenance cost, and the cost of production lost, and extra environmental management cost. So there are some current efforts to solve the fouling deposition and the corrosion problems. So a lot of work has been done to reduce the fouling formation and the control of corrosion. For example, in the recent years, various methods have been deployed to control the fouling as well as the corrosion. And the methods can be classified as the chemical means, for example inhibitors, or mechanical means by changing the phases of the solution, such as for example the electromagnetic fields, electrostatic fields, acoustic fields. There are different catalytic treatment or the surface treatments. Ultimately there are many ways in order to reduce or to minimize the deposition of the unwanted material at the inner surfaces of the heat exchanger. So there are some polymeric materials that have been utilized to minimize or to inhibit the deposition of the different salts at the inner surfaces. So either these polymers are used alone, or they can be used in different combinations. So that's why, for example, acrylic acid and the hydroxypropyl acrylate can be used in combination in order to minimize or to inhibit the corrosion of the metallic surfaces. So the studies were carried out by varying the pH and the surface temperature, and the velocities can also minimize the corrosion of the metallic surfaces. So the investigations reported that the combination of acrylic acid and the HPA and acrylic acid and the sulfonic acid were both very effective in the inhibiting the deposition of calcium phosphate and the corrosion of the pipelines and the metallic surfaces usually used in the process industry. So the one thing is that is very important to know that how the cleaning of the heat exchanger is being carried out. So there are two different kinds of cleaning, that is known as online cleaning and the offline cleaning. So these are the different ways to clean the heat exchanger using online. So while running the heat exchanger, we can just perform some kind of we can circulate different kind of materials in order to minimize the corrosion or to clean the heat exchanger. So these are the different ways by which we can use the online cleaning in order to clean the heat exchanger. So there are some offline ways to clean the heat exchanger, that so we have to shut down the process and then we have to clean the heat exchanger by using these ways, by either by employing the alkaline solution of potassium permanganate, or by cleaning with the small explosives, and or by applying the thermal shocks. There are different ways. You can have a look on this list that can be used for the online cleaning as well as for the offline cleaning. So the last thing is of today's lecture is the fouling factor. Fouling factor must be obtained experimentally by determining the value of U, which is the overall heat transfer coefficient, for both clean and the dirty conditions in the heat exchangers. So the fouling factor is represented by RF, and this is the formula to determine the value of the fouling factor, which is the function of the U dirty, which is the overall heat transfer coefficient when the heat exchanger is in use, and this is the overall heat transfer coefficient when the heat exchanger is clean. There is no deposition at the internal surfaces of the heat exchanger. So this is the list of tables that will give you the values of the fouling factor for different types of fluids, right? So fuel oil will have the value of 0.05 a value of fouling factor. So this is in one unit and this is in second units, so another unit. So you can use either in this unit the value of the fouling factor, and either you can use these units for the fouling factor. So here comes the example that determine the overall heat transfer coefficient U for the liquid to liquid heat transfer through 0.003 meter thick steel plate, which has the thermal conductivity of 5 watt per meter per Kelvin, for the following heat transfer coefficients and the fouling factor on one side. So the fouling factor is only one side. It is mentioned in the question statement. So usually it is on the two side, right? Inside the inner pipe and outside the inner pipe, right? So these are the coefficients for the inner pipe and the outer pipe heat transfer coefficients, and this is the fouling factor only for the one side. And to determine the overall heat transfer coefficient, this is the overall formula, and after putting all the values, right? So H naught is given, K is thermal conductivity in the question statement is given, this fouling factor is also given in the question statement, right? And the HI value is also given. After putting all the values, you will have the value of the overall heat transfer coefficient, which is 8 to 20 watt per meter square per Kelvin. So in this case, no resistance is negligible, right? So everything is countable. So this is one resistance, his second resistance, third resistance, fourth resistance. There are fourth resistances. So after combining all the resistances, you ultimately come up with the conclusion that no resistance is negligible. In the second example, that replace one of the flowing fluid in the example 2.1 with a flowing gas. So H naught, which was 1800 watt per meter square per Kelvin, this was the fluid. So we will replace it with the gas, which is 50 watt per meter square per Kelvin. And after putting all the values, you will get the overall heat transfer coefficient, which is 48, right? So we have just changed the value, which is 1800 to 50, right? So this is the smallest value, right? And it will ultimately, when we solve it, 1 over 50, which will be 0.02. So when we compare the different resistance, this is the smallest value, this is again smallest value, this is also the smallest value, this is the highest value, which is the heat transfer coefficient for the gas, right? So when we determine the overall heat transfer coefficient, so it will ultimately come up with 48 watt per meter square per Kelvin. So in this case, only gas side resistance is significant. So this one is the gas side resistance, overall heat transfer coefficient. So this is the dominant which ultimately give you the value of the overall heat transfer coefficient. So in the next is, if we replace the remaining flowing liquid, which was the internal fluid, is with the flowing gas, which was the heat transfer coefficient 20 watt per meter square per Kelvin, and after putting the values in the same formula, you will have even the smaller value of the overall heat transfer coefficient. And we just after looking at these values, we can just say that the wall and the scale resistances are negligible compared to this value. This is for the internal fluid heat transfer coefficient, and this is the resistance for the outer fluid heat transfer coefficient, which is, and both are the gases in this case. So when we compare these four resistance, 1, 2, 3, 4, so this is for the fouling resistance and this is for the wall. So we can say that these two values are very small and these are negligible compared to these resistances. So ultimately this is the overall heat transfer coefficient for this case. With this, this is the end of the lecture.